objectives of this chapter are to learn the components common to every modern computer system, okay? Be able to explain how each component contributes to program executions, very good. Understand the simple architecture invented to illuminate these basic concepts and how it relates to some real architectures, and know how the program assembly process works. Okay, so the last line is also important. We want to know how an assembly language works. Okay, in chapter one, we presented, as I said, the general overview of computer systems. Chapter two, like data manipulations and like representations. Chapter three, the fundamental of digital circuits. And based on this background, we will start to design a new processor. Okay, so what does CPU do? CPU is central processing unit of each computer, and CPU fetches, decodes, and executes program instructions. I remember that I already explained it to you. What does fetch means? Just getting the data instruction. Just decoding to see what does this decoder, what does this instruction do, and execute this instruction. Okay, we already know this concept. And the CPU has two principal parts called the data path and control unit. Data path and control unit, each CPU. Okay, so of course each computer has memory, I/O, but CPU itself has two parts: data path and control unit. The data path itself consists of few elements. First element is arithmetic logic unit, ALU, which already I talked about it for a few minutes in one of our classes, which gets the input and does some arithmetic calculations like addition, subtraction, and shift on data. And storage unit registers. The storage unit registers, which is inside the CPU. It's not cache memory. The cache memory is outside the memory next to the memory. Okay, sorry, outside the CPU next to the CPU. But register is inside the CPU. Okay, and it's the fastest storage device in CPU, the fastest one. Okay, so what about the control unit? The control unit generates some control signals that these control signals provides the order to different parts of the processor to execute instructions. So control unit is like the boss. It's like the manager. It tells to different parts, okay, you do this, you do that, and like send the signals to different components, what you are supposed to do, what you are supposed to do, and just gives the order to different parts to execute the process and run the software or programming sequence. Okay, so far what we learned: CPU fetches, decodes, and executes the information, the instructions, and it consists of two parts: data path and control unit. Data path consists of two parts: ALU and registers, and maybe some other parts that we will see in detail. And control unit is the manager, which sends the signal to the different parts of the processor. Any question for this slide? Okay. What does register do? Of course, we know register is fastest memory. It holds the data. Okay, so when I say add, let's say this one is an assembler, add 5 and 2. Add 5 and 2. ALU is supposed to add these two numbers. Where are these two numbers located? Yes, at the beginning, where is the original location of these numbers? In the memory. When the instruction is fetched, those data will be grabbed from the memory, comes to the CPU. And in CPU, they will place in the registers. Number 2 is in a one register, number 5 in another register, and ALU gets an order from the control unit, add these two registers together. So ALU gets the value of register A, value of register B, which are 5 and 2, and add them together. And there is an output. Where does that output goes? To another register. And then when it's stored in another register, from that register, it will be like moved to the memory and stored in the memory. Is it clear? Okay, so I already mentioned that registers can be implemented by using D flip-flops. Okay, we already saw the structure. And of course, for 32-bit register, we need 32 flip-flop. Okay, we need 32 flip-flop to have a 32-bit register. ALU carries out like the logical and arithmetic operations as like addition, subtraction, shift, and. So ALU is a part like it's the worker, in fact, like which does the work, the actual work. It's not boss, it's not manager. ALU is like a worker in the level of low level, it just does the operations, okay? And the control unit, which I said that we call it, for example, manager of this structure, the control unit determines which actions to carry out according to the values in the program counter register and the status register. Okay, we will see what are program counter registers and status registers later. Okay, so this one is like the control unit. So I think you have gotten like a general idea about this simple marine processor. Okay, it consists of CPU, and CPU consists of data path and control unit and registers. And any question? Okay, let's move on. Before starting our design, we need some like bus. What is bus? A data bus. From if you want to go from here to your home, you need to drive on roads, on the streets. So bus is like a path to moving data and address and control signals. We need to connect. And so like in processor, those bus are consist of which what are those buses actually? There are wires. There are wires. Okay, those wires are like called buses. Bus, in fact. So those buses consist of wires that is like transfer the signals from one point to the other point. Okay, so yes, but it's not in that level. It's rather in like it's one of the highest level. It's just you mean like the router for you mean the modem? Okay, yeah, it's like the signals, but this one is like in the lowest level. It's not the actual signals, but the router sends like the information with wireless and but kind of yes. Okay, so a bus is a set of wires that simultaneously convey the signal bit along each line. Okay, let's see. For example, if you look at this, let's see. Let's go for example, for this one. ALU to control unit. Okay, so if you look to all this, yeah, for example, you see that this mouse, okay? So this one is like a data bus because it's wires that like convert the data from this mouse to the case, okay? So any like wires that can transfer the data from one point to the other point is called bus. So you see ALU on the left and control unit on the right. You see wires. Why don't we have one single wire? Because if we have one single wire and we want to transfer 8 bits, we need to wait 8 clock cycles. Bit 1, bit number 2, 3, 4, 5. But if we have 8 bits, we can send all of them simultaneously at the same time from pointer. So it becomes faster. and of course more efficient. And two types of buses are commonly found in computer systems: point-to-point and multi-point buses. Okay, point-to-point are buses that connected exactly between two components. So connected, for example, from this example, connected exactly from mouse to the case. That's it. Okay, so those called like point-to-point. But multi-point buses are buses that connected to several different devices, and each device gets like the bus control and use the bus to like send the data and then release the bus, and the other device can get the like bus and send the data. Okay, questions? Okay, what are the like the components of each bus? Each bus needs to have data lines which sends the data. It needs to have control lines, and it also should have address line. What is data line? Of course, data line is data. The data will be transferred from one point to the other point. What is control line? The control line, the value of the control line determines the direction of the data movement. So if we have two point A, point B connected with bus, so this control line tells that we want to send data from point A to point B or from point B to point A. Okay, so determines the like. And of course, the address line is very important. If we're dealing with memory, the memory has like a different address locations. It says that, okay, we have the data. Okay, data is ready. The direction is ready. We want to send it from ALU to the memory. What else? What is missing? The address is missing. Which location of the memory we want to place this data? So we need to have data line, which includes the data. We need to have control line, which determines the direction. And of course, we need to have an address line that determines the location of the data we want to place or we want to access and get the data. Okay. So those are those are the like lines and lines that we need to have in a any bus. Here is an example. We have CPU, we have main memory, and we have I/O devices. And if you see, we have address line. In the first group are address line, the second group are data line, and third group is control lines. And this bus can connect CPU to the memory to the I/O devices. Okay, so it's example of a bus. It's just an example. It's like not very accurate. Any question? Okay. And here also we have a multi-point bus. So we need to have a protocol to determine okay, this one multi point bus. So you see that the CPU is connected to memory, connected to this controller, connected to monitor, and other devices. Okay, and so we need to have a protocol. What does protocol determines? Determines that how different devices can get access to the bus. Okay, and after discussing the bus and main components of a CPU. It's time to see what is the clock cycle, which we know. But again, let's do a review. Every computer contains at least one clock. That why we need that clock? In order to synchronize the activities of the computer components. We need to clock. So we need to like give them like timeline. Okay, it's your turn, it's your turn, it's your turn to do any like task. Okay, so by the way, if you remember, I said add 5 and 2. Okay, it can't be done in one clock cycle. It needs certain time of clocks. In one clock, for example, in one clock, data will be fetched from the memory. In second clock, data will be stored in the register. In the third clock, ALU will access to the register. In the fourth clock, ALU will add them. In the fifth clock, ALU place the result in the register. So we need like a fixed number of clock cycles in order to carry out each data movement. Okay, so each data movement or computational operation requires the fixed number of clock cycle. And by the way, let me give you one small to tell you one small point. This fixed number of clock cycles is not true anymore. It's for old computers. For new computers, each instruction has a different clock cycles. Okay, so one instruction is simpler, takes you only one clock cycle, two clock cycles. One of those like floating point might take 20 clock cycles. But in the simple versions that we learn here or in like other classes which we deal with simple computers, CPUs, all of those are the processors that needs the fixed number of clock cycles to do any operation, regardless of operation type. So if we want to add two numbers, if we want to shift a number, if we want to move a number, all of them, for example, takes 5 clock cycles. But in new computers, it's not the case. Okay, in modern computers, each instruction has its own clock cycles. And each clock has a parameter called the clock frequency, which is like measured in megahertz or gigahertz. Of course, nowadays it's like a gigahertz that determines determines the speed with which all operations are carried out. Why determines? Okay, faster clocking, faster operation. If it needs 5 clock cycles to add two numbers, so faster clock cycle is faster operations. Okay, so of course it's obvious. And by the way, we know that reciprocal of the clock frequency is called a clock cycle. So if we have a clock like this, if the frequency is 10 hertz, one clock cycle takes 1/10 seconds to like is 1/10 seconds. Okay, so frequency is 1/period. The period we can also call it clock cycle. Okay, frequency is 1/period or clock cycle. But here the point, here is the point. The clock cycle is not the only parameter that determines the CPU performance. So you cannot say that a faster clock cycle means better computer, okay, or better processor. And it's said here, it says that the clock speed should not be confused with the CPU performance. It's different, okay? It's one of the parameters that determines the CPU performance, not the only one. Okay, we have one thing called CPU time. What is the CPU time? If you remember, I said that uh, each instruction needs a certain time of clock cycles to be executed. Okay, so The CPU time is the time that the CPU needs to execute a program. Okay, let's see an equation together. So let's see how does we can define the CPU time. The CPU time, how many seconds per program? How many seconds per program? So we have like a benchmark program. We want to see how many seconds it takes this program to be run. Okay, so how many seconds per program? I want to expand. Okay, by the way, we know that A over B, A over B. I can write it in this way, A over C times C over B. Is it right or wrong? Of course, it's correct. Or I can say A over B is A over C times C over D times D over E times E over B. It's same, okay? So if we multiply C cancel C, D cancel D, E cancel D, and the same thing here. So we say the CPU time is the second per program. I want to expand it. I say how many instruction is we have per program? How many instructions per program? Times how many instructions per program times how many average cycles we need per instruction, how many average cycle we need per instructions, times how many seconds per cycle. Okay, if we want to simplify this one, this instruction will be cancelled by this instruction, this average cycle, this cycle, and what is the seconds per program. Okay, so each term has a meaning. Each fraction has a meaning. The first one says that how many instructions we have in a program. How many instructions we have in a program. The second term says that how many clock cycles we need per instruction. And the third term says that how many seconds we need per cycle. What's the clock cycle? Okay, so if we multiply these three together, the result, the outcome is the CPU time. The less CPU time, the faster calculations. Okay, so the CPU time or the performance, it's not only determined by second per cycle, it's also determined by these two. Okay, if I tell you that I designed a new computer, okay, let's see, for example, Kevin designed a computer which worked with 100 megahertz. Okay, for example. And I say, okay, Kevin, I designed one which can work with 200 megahertz. Okay, mine is faster. Okay, fine. But when we go to the detail, I see that his computer, in order to a task, need 100 instruction to do a specific task. But mine, because it's a different instruction, mine needs 400 instructions. Now his design is better than mine because his design also, it's correct that it's 100 hertz, but only 200 instructions. But mine is 2 hours faster than, but 2.5 times more instructions. Okay, so all this, is it clear? Okay, all these three parameters together determines the performance, not only one of them. Okay, so for example, in other words, if you say, okay, I've designed a computer that needs like half of the instructions that my computer has. Okay, half of, that's fine. But you say, okay, but we have a limitation. It gets very hot and I have to reduce the clock cycle by 4 times. So which processor is better? Of course, mine is better because you have to like reduce the clock cycle 4 times more than mine. Even your instructions are half, but your like speed frequency also 1/4. Okay, so the multiplication or product of these 4 terms determines the frequency, the instructions. Okay. Okay, that's enough. Okay, but few things. That's enough for the class. But let me just don't leave the class. Just let me just turn off the recording.